Welcome everyone for this VLSI design lecture series. In today's lecture video, I'll be discussing about constant voltage scaling and small geometry effects. While the full scaling strategy, which was discussed in the previous lecture video, dictates that the power supply voltage and all the terminal voltages be scaled down proportionally with the device dimensions, the scaling of voltages may not be very practical in many cases. So as we have discussed about full scaling in our previous video lectures, we have understood that all the parameters will be scaled down, including voltage. Scaling down of voltage may not be very practical in many applications. In this particular scaling called as constant voltage scaling, all the dimensions of MOSFETs are reduced by a factor called as S, as in full scaling. The power supply voltage and the terminal voltages, on the other hand, will be untouched or will remain unchanged. So we already know this particular expression. COX dash is equal to epsilon OX divided by TOX dash. The COX dash is nothing but oxide capacitance after scaling, which is equal to epsilon OX, which is permittivity of oxide, divided by TOX dash, which is the thickness of the oxide after scaling. So we already know that the thickness of the oxide after scaling TOX dash is given as TOX divided by S. So this S goes to the numerator, so it will become S into epsilon OX divided by TOX. Epsilon OX divided by TOX is nothing but oxide capacitance. Hence, COX dash, which is the oxide capacitance after scaling, is equal to scaling factor multiplied by normal oxide capacitance before scaling. So using this expression, let us try to find out how the drain current will change for this constant voltage scaling. So now let us consider this equation for drain current ID under linear region of operation. So under linear region of operation, we already know that ID linear is given with the formula COX mu W divided by L into VGS minus VT into VDS minus VDS square divided by 2, where ID is nothing but the drain current under linear region of operation, COX is the oxide capacitance, mu is the mobility of electrons or holes, W is the width of the MOSFET, L is the length of the MOSFET, VGS is the gate to source voltage, VT is the threshold voltage, VDS is the drain to source voltage. So now let us try to consider how this scaling affects our drain current under linear region of operation. So ID linear dash, which is the scaled drain current under linear region, is equal to COX dash into mu into W dash divided by L dash into VGS minus VT into VDS minus VDS square divided by 2. Here, if we observe in constant voltage scaling, as the name itself indicates, the voltages will not be scaled. Hence, the voltages is untouched. The voltage is not scaled. And as I discussed in our previous video lecture series as well, this mobility of electrons or mobility of holes is assumed to be constant. Hence, even if we scale down the MOSFETs, we assume that the mobility is not affected. So ID dash linear is equal to S into COX, because COX dash is nothing but S into COX, which we have just seen in our previous section, into mu into W dash is nothing but W divided by S, L dash is nothing but L divided by S. VGS minus VT into VDS minus VDS square divided by 2. S and S will get cancelled. Scaling factors gets cancelled. And finally, we'll be left out with this expression. ID dash linear is equal to scaling factor multiplied by oxide capacitance multiplied by mobility of electrons or holes multiplied by width of the MOSFET divided by length of the MOSFET, the length of the channel, into VGS minus VT into VDS minus VDS square divided by 2. Let me consider this as equation number 2. Now, equation 1 and equation 2 we get. So let us see what is equation 1. Equation 1, we are already familiar with what is equation 1. The formula of the drain current under linear region of operation. So this particular equation 1, in equation 2, we get this particular expression. ID dash linear is equal to S into ID linear, where ID dash linear is nothing but the drain current after scaling. S is the scaling factor. ID linear is nothing but the unscaled drain current under linear region. Similarly, if we consider one more region of operation of MOSFET, which is saturation region, ID saturation dash is given as S into ID saturation, where ID dash saturation is the expression for current or the drain current under saturation region for scaled or after scaling is done, which is equal to S into ID saturation, where S is nothing but scaling factor, ID saturation is nothing but unscaled drain current under saturation region. So now we have understood how the drain current expression varies for constant voltage scaling. Similarly, let us consider power dissipation. So we already know that power is given by the expression V into I, voltage multiplied by current. With respect to our MOSFET, power is given as VDS into IDS. Drain to source voltage multiplied by drain to source current gives us the power of MOSFET. P dash is equal to VDS into IDS dash, where P dash is nothing but the power after scaling. VDS remains unchanged because voltage in this particular scaling, the voltage is maintained constant. Hence, this VDS remains unchanged into IDS dash. IDS dash is nothing but the drain to source current after scaling. So P dash is equal to VDS into S into IDS. This S into IDS we have just seen in our previous section how we got that. So P dash will be equal to S into VDS into IDS. This VDS into IDS is nothing but the power. Just in the previous section we have seen power P is equal to VDS into IDS. Hence, if we apply that in equation 4, we get P dash is equal to S into P. That means the scaled power is equal to scaling factor multiplied by the unscaled power. So if we observe this equation number 5 carefully, we can conclude that the power dissipation is increased by a factor called as S in constant voltage scaling. Now let us discuss about short channel effects. The MOSFET can be defined as a short channel device if its effective channel, L effective channel length is approximately equal to the depth of source and drain junctions, which is given by X subscript J. Channel length is nothing but the distance between source and drain. If the distance between source and drain is approximately equal to the depth of source and drain junctions, then we can call that the MOSFET is a short channel device. These effects can be divided as drain induced barrier lowering, surface scattering, and hot carrier injection. So when we consider MOSFET as a short channel device, these three effects can be seen in a MOSFET, which is drain induced barrier lowering, surface scattering, hot carrier injection. So let us see what all these effects are one by one. Let us first discuss about drain induced barrier lowering. Under normal condition, when the drain to source voltage is equal to 0 and the gate to source voltage is also equal to 0, there is a potential barrier called as threshold voltage which stops the electrons going from source to drain. That means when we are not giving any potential, any voltage between the gate to source voltage, gate to source junction, and we are not giving any potential or voltage between drain and source regions, we have something called as threshold voltage, a potential barrier called as threshold voltage, which stops the flow of electrons from the source and the drain regions of a MOSFET. The gate voltage, when it is increased above the threshold voltage, a channel is formed, a connecting path is formed between source and drain regions, and hence there will be flow of current between the drain to source. There will be flow of electrons from source to drain region, and conventional current is always assumed as opposite to the flow of electrons. Hence, the current flows from drain to source region. However, as a channel becomes shorter and shorter, a larger drain voltage widens the drain depletion region to a point that reduces the potential barrier. This effect is called as drain-induced barrier lowering. The name itself indicates, because of the increase in the voltage of the drain to source, the barrier, that is the potential barrier, gets lowered. This effect is called as drain-induced barrier lowering. And this is one of the short channel effect which is seen in our MOSFET. In addition to this, we have something called as surface scattering. So this surface scattering can be understood with the help of this diagram. When the charge carriers travel along the channel, they are attracted to the surface of the electric field created by the gate voltage. So when these particular electrons, as I told you, electrons starts to travel from source to drain. So when the electron starts to travel from the source to drain, when some amount of voltage, gate voltage is applied to it, say positive gate voltage is applied to it, only then channel is created. Channel is nothing but the connecting path between source and the drain terminals. So when some positive gate voltage is given, there is a formation of channel and the electron starts to flow from source to drain regions. So when this happens, because electrons are negatively charged particles, they start to get attracted towards the gate terminal because we are giving positive input, positive gate voltage towards this particular terminal. These electrons starts to get attracted towards the gate region. So as a result of this, they keep on crashing and bouncing against the surface during their travel, following a zigzag path. This effectively reduces the surface mobility of carriers. From the figure, if we observe, it is very clear that as electrons travels through the channel, it is attracted towards the gate and again bounces back, again gets attracted and bounces back, gets attracted and bounces back. This is called as surface scattering, and which affects the mobility of electrons or mobility of holes. And one more short channel effect which is seen in our MOSFET is hot carrier injection. So this hot carrier injection can be understood by this particular diagram. Advances in VLSI fabrication technologies are primarily based on reduction of device dimensions, such as channel length, the junction depth, and the gate oxide thickness, without proportional scaling of the power supply voltage. This scaling results in a significant increase of horizontal and vertical electric fields in the channel region. Electrons or holes gaining high kinetic energy may be injected into the gate oxide and cause permanent damage to the oxide, which in turn degrades the current voltage characteristics of MOSFET. So if we observe this particular figure, it is very clear. Whenever we apply some positive gate voltage, a channel is created between source and the drain regions. So when channel is created or when path is created between source and drain regions, the electrons can flow from source to drain region. So when the electrons are flowing from the source to drain region, some of these electrons, because electrons are negatively charged particles, according to the law of charges, and like charges will attract and like charges will repel. So because this negatively charged electrons gets attracted towards the gate, some of these electrons may even perforate the oxide and they can directly enter into the oxide or it will directly enter into the oxide. This phenomenon is called as hot carrier injection. And this is one more effect which is seen under short channel effect. I hope you have understood the concept. Thank you.